All right, let's take a look. Let's take a look at your book assignment here. Let's run through the answers to the matching. Now, if we look at and before we get into this completely, let me just jot down the three main components of what you need to be able to do in section 4.1. Now, some of you did not get much practice on the Newton's Law of Cooling, 23 and 24, it looks like. And that is guaranteed to be on it. Okay, guaranteed to be on the quiz. You're going to have to be able to do that. So that is one of the things. You know, we probably won't do any more of those before the quiz. But that will certainly, I mean, we might do another one. Maybe when we review on Wednesday, we'll probably go through that. So you have to be able to do that problem. You need to be able to draw, which we're going to focus on a little bit today, a slope field. And you're going to need to be able to do the matching with the slope field, or I guess slope fields. Match slope fields to their differential equation, or as you some of it we'll do today, match it to the original function. So those three things are what we need to be able to do from section 4.1. Now 4.2 is going to get into limits, and we'll start with that on Monday. We'll spend Monday and Tuesday working on those things, okay? Which is some stuff we did back in chapter 2. So if we look at let's do the matching problems first. So if we look at number 7, which would, okay, go back here, work our way through this. So we talked yesterday about how you have to be able to, one thing that would be helpful is to look at a slope field and tell if the differential equation would have just a y in it, or just an x, or both. What's this one? How do you know? I'd like to hear in your words, how do you know that this one's going to be just a y? Spencer. So you just kind of memorize that. If it's based on rows, the pattern is based on rows going across. In other words, when you go across, they're all the same. That's y. What do you use to help you remember rows as y? Okay, the equation of a line y equals 1, or y equals 2, or y equals 3 is a horizontal line. So associate that with y. Okay, anybody else? Have a different way, Calvin?
Well, I just remember that, like, if the slopes are constant for any value y,
then it's for y. So if the slopes, as you go across, if the slopes are constant at a y value, then it has y in it. Okay? Anybody else have a different way of thinking? I mean, whatever works for you is fine, right? I mean, some people will say that if you guys were all doing a horizontal thought process, another way of thinking about it is as I go down this way, the y's are changing, right? As I go down, the y's are different, right? As I go down, the y's change and the slopes change. So that's a match as well. When the y's change, the slopes change, so therefore there must be a y in there, okay? But as I go across, the x's change. Well, here, as the x's change, the slopes don't. So there must not be an x, because every time you get a new x, you should get a new slope, and you don't there. So there's all types of different ways to think about that. So this one has to have a y in it. So then, once you've done that, then you've eliminated some of those choices. So in this particular one, there was 10 different choices we had to pick from, but only 3 of them had just a y in it, I think, right? One was this, and one was this. Correct? Those were the only 3 that have just a y in it. So then you pick a point. So this point right here, 0 is always a good one to plug in. So here y is 0. So you do cosine of 0, that's 1. Looks like y prime would be 1, the slope. Put a 0 in here. 1 minus 0 is 1. Oh, okay, so that's a possibility. Put a 0 in here. You'd have 0 times 1, which is 0. Definitely the slope is not 0, so you eliminated this one. Now we need to pick another point. So we try this one up here. Maybe y is 3 up here. Cosine of 3. Well, 3 is really close to what? Pi. So how about we do cosine of pi, which would be what? -1. Cosine of pi would be -1. Oh, that looks pretty good. Put a 3 in here. 1 minus 3 is -2. Now, could that be -2? It's not very steep. It doesn't look like it would be -2. But that's almost too close for comfort for me. I think I would try another one. So if I tried this one, where y is -3, so cosine of -pi would go this way. That'd be same as pi, actually, wouldn't it? So that's -1, which looks reasonable. And I put a -3 here. I get 1 minus -3. That'd be 4. Definitely slope is not 4 there. And so that rules it out for sure. And so we get that. Okay? So that's how you do it. So you kind of eliminate it based on whether it has x, y, or whatever. And then you would plot some points to see if the slopes match. Okay, so quickly then running through. 8 was Roman numeral what? Roman numeral 1. Number 9 is Roman numeral 3. Number 10, Roman numeral 4. Now this would have both x's and y's, right? Because, again, as you go across or you go down, they change both ways. So Roman numeral 4. Number 11 is Roman numeral 8. Number 12 is Roman numeral 9. 13 is 10. And the last one was 6. The last one was 6. Now, one thing to keep in mind, notice here on number 6, Roman numeral 6, you've got y prime equals -y over t, which is kind of what I have here. I put an x in, I guess, accidentally. But -y over t or -y over x. Now look at this slope field. At 0, 0, what do you get if you put 0, 0 into this? Undefined, but a special type of undefined, right? We talked about that being indeterminate. In other words, there could be some, when we were doing limits, there could be some value. So something special was going on there. Well, you notice there isn't any slope there at all. Typically what's going to happen is the curve's not going to go through that point at all. But what about at, say, this point right here, 0, 1? What about the point 0, 1? Well, then you get -1 over 0. Well, that's also undefined, but what did we say when we were talking about limits that happens if you have a number over 0, like 2 over 0? Vertical asymptote. So that would be a vertical slope. So when you go to draw your slopes, if you get a number over 0, that's a vertical segment. So you would draw a little vertical segment for that. Now if you get 0 over 1, that's of course horizontal segment. That's slope 0. But if you get 0 over 0, don't draw anything at all. Okay? There wouldn't be any slope segment there at all. So that'll come into play today when we draw some of our slope segments. Okay, so let's go ahead and move to number 23 now. And we're not going to go all the way through this, but basically you have to know, if you're doing a Newton's Law cooling problem, that you're working with this solution right here. Okay? Yes, this is the differential equation. Y prime equals k times y minus t. And you need to know that. And you need to know that these go together. But if you're asked to work out and answer questions about a problem that involves the temperature and the cooling kind of a situation, then this is what we want to use, the solution to the differential equation. All right? So, this is really not going to be of much use to us right here as we go through these problems. All right, so you were told that the coffee started out at 90. Oh, by the way, did anybody catch the Boris and Natasha reference in there? The problem 23? Anybody ever watch Rocky and Bullwinkle? Ever heard of the Rocky? It's a cartoon with a moose and a... Okay, well anyway, Boris and Natasha are kind of their enemies. They're the bad guys. Anyway, all right, so that's kind of an old old person's reference, old people reference, I guess. All right. All right. So there are 4 different equations you have to end up dealing with here, based on the fact that Boris uses a cardboard cup and Natasha uses a styrofoam cup, so they have different K values, and then they also go outside the coffee shop and they're inside. Okay. So when they're outside, you have -10 plus A you don't know, at least at the beginning, and let's just use Boris first. His was -0.05, and then the T. Okay? Now how do we find what A is? We have to put in the initial condition. Now once you do a few of these, you start to get the hang of what's happening, but you put a 90 in there, and then this becomes just e to the 0, because when you put a 0 in for t, it doesn't matter what k is, because you're going to get e to the 0, and e to the 0 is just 1, so a ends up being 100. So in the bank interest formula, where we didn't have this t here, the a was just the initial amount, right? Whatever it was at time 0, that was a. Well, it's kind of close to that here. The a is related to the initial temperature. It's not the initial temperature, but it's actually the initial temperature minus the surrounding temperature, right? Because that's what's going to happen every time you put a 0 in for t. This part's going to go away. You're going to subtract that over, which in this case would be add that over, subtract the -10. You're going to get 100. So you're going to get an equation that is, for Boris, that would be this. And Natasha's would be the same, except she's going to have a -0.08 in it. And then when they go inside the store, what's going to change? -10 will be 25. And what's the 100? What's the 100 end up being when they go in the store? 65, right? Again, you have to put your initial condition in and you get that. So you've got 4 different equations to handle those situations. All right? So you've got to do that. If you haven't worked these yet, then you need to go back through and you need to do that. But now, then it wants to know, how long does it stay above 70? So what do I do? Let's just use Boris's here. Put 70 right there. Y is the temperature. Now at this point, you can simply go to your calculator and you can solve it, right? You need to know how to do that. Go to the menu in the calculator screen, go to solve, algebra solve, you type that in and you solve it. Now it's probably going to give it to you, well, it should give it to you as a decimal because you got the negative. When you have a decimal in the problem, it usually spits out a decimal. If it spits out a natural log, I would hit Control Enter to get a decimal. Okay, so what did his end up being? 4.46 what? 29 or 463, 29 be fine too. So his takes that long. Hers was 2 point something. 7, 8, 9. You should always do 3 decimal places. Anytime you give a decimal answer, you should do 3 decimal places. I saw several people with only 1 or 2 decimal places. Of course, that's what the back of the book had, I think. You got to have 3. Okay? So hers was in cardboard, his was in styrofoam. The styrofoam insulated much better, so that different K value meant his was going to take longer to drop down. His didn't cool as fast. Okay? All right. So then when you go to the outside, well, no, then there was a second question. After 5 minutes, right? Well, there you don't even need to solve. All you do there is take your equation, put a 5 right there. Put a 5 right there, right? And so after 5 minutes, his was down to, what, 60-something? 67-something, and then hers was down to like 57-something, or 56 point something, or whatever, somewhere in that neighborhood, okay? So, hers is dropping faster because her cup is not insulating there as much. All right, and so then when you go to the outdoors, indoors, then those numbers change, and then you rework it again. So just be able to solve, be able to plug numbers in for t, that's really all this is about. All right, and then the last part, part C, wanted to know what K value would keep it at 70 degrees. Was it for 5 minutes? Was that what it was? So then you just do 70, negative 10. Was it outdoors or indoors? Outdoors. So negative 10 plus 100 e to the k times 5, and then you just solve that. Just solve that on your calculator for k. And it was something like negative 0.0446, something, I think. Something like that. At least that's what I remember last period they were talking about. Okay? All right. And then 24, just to check, I suppose, the answer. What did you have for that one? It wanted to know what was the situation there? They wanted to. That was another cooling situation. How long it stays above 100? So what'd you have there? 30. 30. The book here says 30.5 something. 30.527. 30.527. Okay? All right, so we'll have some work time here later, and if you've got some more questions about that, we can talk about it. But that's about all there is to it. That's about the only other question that we could ask about this situation might be how fast is the coffee cooling? At 5 minutes, how fast is it cooling? Like in degrees per minute. Right? So what would you do? If we were going to take Boris outdoors, how fast was his coffee cooling at 5 minutes? What would you do? Derivative, right? The derivative of this equation, y prime. Now, you might think, well, what about the differential equation? You could, but the differential equation, remember, doesn't have little t in it, right? You'd want to use this equation and find the derivative. So you could do the derivative of that equation. That's y prime. That's the rate of change of the temperature, and answer that question. Then plug a 5 in, basically. How fast is the coffee cooling in degrees per minute? Yes.
Use both equations, honestly, because like the differential equation had a y in it.
Yes.
Put the 5 in there and then put that y value.
Great point. This is okay. So for Boris, the K is this, and what was our temperature? T was negative 10. So this would actually be this, right? All right. And then if you did the derivative of Boris's equation, and did this one, you'd have two different y primes equations, but they are the same y prime. That's right. So you absolutely could do this. So at 5 minutes, so if they wanted to know at 5 minutes, if you did the derivative of this one, you'd plug a 5 in for t. If you want to use this one, you'd have to find what was y at 5 minutes, which I think we did actually in this part of it, and plug that in, you should get the same exact answer. Yes, so you could use it. It's just that a lot of times this one isn't as useful, but it certainly is the same y prime, so that would work. So that's a great point. All right? So otherwise, that's about it. I think about what they ask you. What is the temperature at a certain time? At what time will it be a certain temperature? What K value do you need to keep it a certain temperature at a certain time? Really, that is pretty much all the different unknowns that you could possibly do. And to get the A, you have to use the initial temperature. That's it. So be able to work with a problem like that. All right, so what we want to do next, go ahead and get that document, your calculator, and the document I sent you. It's called Slope Fields Forever. Now, that's another old person reference. You music people should know this. Strawberry Fields Forever, the Beatles, right? Famous song by the Beatles. Anyway, I didn't name this document, but that's where that comes from. All right, so this goes with a worksheet that we have right here. And this is what we're going to be working on today, a couple different things. Now,
I think that was a really good one.
all right. Now, this, my intent, if we didn't have so many people gone, was for you to answer these questions in the document, and then I was going to collect it back.
Ooh, that's cool.
But we have so many people gone, I'm not sure it's... So I still might just to try it on Monday, but but you don't have to answer them in the calculator. So a lot of this worksheet, really, you don't really need the calculator document I sent you. Okay? There are a couple of questions where they give you some multiple choices, so you might want to use those. Okay? So the first thing they do is they direct you here to go to page 1.3. So 1.1 is just a title page. So 1.2 just says slope fields provide a graphical method to find a particular solution in a differential equation. It depends on the initial conditions. Grab the initial condition and move it about, and this is the slope field. Okay, so if we go to the next page, all right, whoops, I went too far. So here is the slope field, and the initial condition is right there at about 0, 1, looks like, the red point. And you can see that this kind of goes with the flow. Oh, you know what? I'm sorry, I forgot something really important here. Let me back up a second. This, let's find a good one here. Okay, here'd be a good one. On your book homework, everybody look on the screen up here real quick. On your book homework, the direction, I didn't tell you to do this, I wasn't expecting you to, but the directions of that matching said that you also were supposed to draw a sketch of the solution curve through the blue dots. I will do that. I will ask you to do that on the next quiz. So if I give you a matching set of problems and I have some slope fields, then I'll also probably ask you to sketch in the solution curve as well. So if this is the initial condition right here, then the solution curve for this, you just kind of go with the flow from this point, which would be kind of going down like so, and then it seems to level off, kind of a horizontal asymptote. Then this seems to come up, but then it kind of levels and switches and kind of comes back down, and then seems kind of a bell-shaped thing. And that would be the solution curve for that one. Okay, these down here would be down on this end. Okay, or take another one, for example. Okay, take this one here. Okay, this one seems to, okay, would kind of go and follow those. Kind of goes up. And then follow those like that. So when I grade that, there's some leeway there as to how you draw them and how accurate they are. Now here would be case number 7 here. This has asymptotes as well. This one, if you're doing this one, this kind of comes down here and then would level off. So that's pretty simple to do, and I want you to be able to do that. You're going to do that on some of your homework today. Okay, so back to this. So this just kind of goes with the flow of those slopes. Now, if you can grab this, they tell you to describe your observations when you grab this. Now, yours is going to go a little slower than mine probably when you try to grab this. Mine's redrawing probably faster than yours. But, you know, the point is, when you move the initial condition to somewhere else, when you move the initial condition, that changes what the potential solution curve looks like. Okay? And that's really all they wanted you to answer on number 1, that you have different initial condition is going to have a different solution curve, and it's going to follow the slope segment. Okay? So then the next page, so you go over to 1.4 and it says, okay, here's this slope field, has many short segments. Find the value of the slope at these points, and it gives you 4 different points. And down at the bottom of this page, it gives you a place that you can type them in. Now, I don't care if you do or not. I want you to write them on your paper for sure. So question 2, 3, and 4 are on here. Okay, now all you really need to do to find the value, how do you find the slope at -1, -1? Here's your differential equation right here. You just plug them into that, right? I mean, you can probably do it in your head or go to the regular calculator screen, just hit the scratch pad and go to, and just do it right here, right? So put a -1 in, put a -1 in for x. Okay, put a -1 in for x, put a -1 in for y, and just calculate your slope. That's all they want you to do. Okay? The next question says, for this differential equation, when is the slope of the tangent 0? Now, on your paper, it doesn't give you options, but on here, it gives you options where you could select. So put it on your paper for sure. If you want to answer it on the calculator document as well, you can. Okay, and so forth. Now, when you get to the bottom of the worksheet, it says part 2, and it goes through this whole description of how you could, if you look at the back is a matching activity, like we did today, all right, which is something you're going to have to do in the quiz. It says that if you wanted to, you could graph these and use it to kind of check your answers. That takes quite a while to type all those in and look at them. So if you want to, go ahead, but you don't need to. So the back you could just do as a matching. You don't need to use your calculator. Okay, because quite honestly, on the quiz, that's how it's going to be. You're not going to get to use your calculator for the matching. All right. So last thing I want to do with you is your second worksheet. And this is the other part of what we need to be able to do, and that is to draw a slope field. Okay? And so on this worksheet, there's going to be some drawing, and there's also going to be some matching practice as well. So you should get plenty of matching practice before we're all done. Now make sure when you get this, it has 2 pages. I noticed some of the staples didn't. Some of these didn't staple correctly. Okay, so make sure you got 2 pages on this. All right. Now, let me make a couple of comments on this. If you turn it over to the second page, okay? You turn it over to the second page. The first page, we're going to draw some slope fields. We'll do one together. The second page has a matching, but this matching's a little different. What do you notice about your list of equations on the back of the first page? It's not y prime, it's y. Remember? And slope field is the y equation. I mean, these graphs are the y graphs. When you look at a slope field, these are the slopes of y. So it's the y graph you're looking at. So on this one, it actually should be easier. When you do y equals sine x, you're looking for the slope field that actually looks like sine x. Okay, so you don't have to do as much as far as plotting points and so forth. Now the back page is more like what we've looked at. Here's a slope field, and then you're matching it to its y prime equation. Remember, dy over dx is the same as y prime. Okay, so that's some more matching there. All right, let's go ahead and do number 1 together here. This is kind of what your thing will look like on the quiz. I might make you do a few more points, but probably I can make you do more than about one of them. So you got some of these that have just x, some of them that have just y. Those are easier to do. The ones that have both x and y take a little longer, because then every point you have to plug in, right? Like on this one, let's just do this first one together. So we get, remember, dy dx is just the same as y prime. So on this one, when I put a 0 in for x, I get a slope of 1. Well, that means every time x is 0, I get a slope of 1. And so I can get all 5 of these with just one calculation. Unfortunately, when there's an x and a y in this differential equation, you got to do point by point. So it takes a little longer. Okay, so there's a 0 in for x. Now let's put a 1 in for x. We get 2. So now it's a little steeper. And, when I'm grading these, I'm looking at, like on the quiz, I'm just looking to make sure, okay, does it get a little steeper? Is it reasonable? But if you've got a positive slope that's supposed to be negative, or you've got a diagonal that's supposed to be horizontal, that's going to get counted off. All right, then we put a 2 in. 2 plus 1 is 3, so that's steeper yet. And once you get slopes above 3, 4, something like that, then it gets pretty hard. Then they're almost vertical. Put a 3 in, you get a slope of 4, so now it's really getting steep, right? And so just do the best you can with those. Okay, and then we come back here to -1. -1 plus 1 is 0, so these should all be horizontal. right? When x is negative 1, it'd be horizontal. When x is negative 2, it'd be a slope of negative 1. So kind of a 45 degree. And then when x is negative 3, you get negative 2, which is steeper yet. Oops. Okay, and so what do you look like? What's it look like? What's your y equation going to be? The parabola. You can kind of see that parabola in there. And of course, this is one of those we could do the antiderivative on. If we want to do this y prime, do the antiderivative, this would be an x squared. And so this would be a parabola. Okay, so that is what you're doing on that front side. So you're going to draw slope fields there. You're going to do matching on the other two pages. You've got your other worksheet there, and you've got the last 40 minutes to work on it. Okay?
So we're gonna get this done as
I think you should. And that is your whole assignment for